Swayam Prabha. Digital India. Educated India.
Okay, good morning. Today I want to discuss with you about the evolution of fuel injection systems, especially for the spark ignition engines. So, in this today's lecture we will be discussing about the conventional fuel injection systems that we have been using for almost a century now, more than a century now, that is the carburetor, and then the evolution into the next generation fuel injection equipment, which is port fuel injection system, and then the latest addition to this series will be gasoline direct injection systems. So, today I will be covering some of these aspects. So, you see, if you look at the history of fuel injection system development, always the people who designed the IC engines in the beginning, Nicholas Otto, etc., they always had this dream that can we really inject the gasoline directly into the engine cylinder, and that will help us achieve very high efficiency similar to diesel engines, and then we will also be able to cater to different power output, very high power output from the petrol engine. But that did not happen because petrol requires more time to evaporate in the combustion chamber, and then the combustibility, auto ignition temperature, etc., is also very high. And so, in order to achieve the combustion with petrol, what is required is that really you mix the fuel and air to form just the right quantity of fuel air mixture. You control the timing and position of the air fuel mixture in the combustion chamber, and then at the right time you apply the spark. So, that has to be done, and for almost 100 years we could not do it because of variety of issues. So, it is possible only in last like 20-25 years that lot of electronics was introduced, and that made it possible to achieve basically control on all these processes. So, Mitsubishi company from Japan is one of the lead companies which has developed this technology, and they are the pioneers, and then after that of course, there are a lot of other automotive companies which have sort of developed one or the other variant of this technology, and we will be discussing, we will be looking at some of these aspects. So, coming back to very general aspects, there are many global issues such as and there are many local issues related to pollution. There is a requirement for greenhouse gas reduction, and when we talk about greenhouse gas reduction from the gasoline engines, we always talk about increasing the fuel efficiency, so that for the same kilometer travel you are actually burning less amount of fuel, and therefore, you are putting lesser amount of carbon dioxide into the atmosphere because of the combustion of hydrocarbon fuels. So, therefore, any efficiency improvement initiative for increasing the efficiency, thermal efficiency of the gasoline or diesel engine really helps in addressing the global issues of GHG emissions. It also helps us in addressing the local pollution issues, because if you have an engine which is running efficiently, so obviously it will be putting out lesser amount of carbon monoxide and lesser amount of hydrocarbons into atmosphere and lesser amount of NOx. So, if you can achieve the reduction of all these three by making efficient engine, so you not only address the local issues, but also you address global issues, and GDI technology is technology which addresses both of these to a large extent from SI engines. So, coming to CO2 reduction, there are many technologies that are available. They enable major reduction in CO2, but sometimes what happens is that these carbon dioxide reduction technologies require a very heavyweight engine, or there are many additional subsystems that need to be incorporated into it. And what happens is that when you want to manufacture those components or those subsystems, you end up putting more amount of carbon dioxide into the atmosphere than they will be saving over a lifetime. And then you also put in lot of CO2 into the atmosphere when those components are recycled at the end of the life. So, so that is one major issue, and GDI engine does not require any major alterations. So, the beauty of GDI engine is it does not require any many number of alternate systems, additional systems. Their design is pretty much similar to conventional engines. So, when you produce a GDI engine, you are actually consuming almost similar amount of, you are actually producing almost similar amount of CO2 and putting into the atmosphere. So, global CO2 that you are putting in is almost similar, and since GDI engine is far more efficient than conventional port fuel injection engines. So, therefore, you are putting less amount of CO2 into the atmosphere during the usage time. So, that way you can actually reduce significant amount of CO2 that is being put into the atmosphere in lesser quantity. Then there is the issue of reducing carbon monoxide, hydrocarbon and NOx emissions. So, as I said, Mitsubishi company is developing the GDI and they are meeting most stringent emission norms. They basically take a lot of, they use lot of features, they have incorporated lot of features in the GDI engine, which enables huge amount of reduction in carbon monoxide, hydrocarbon and NOx emissions. So, some of these features include earlier activation of the catalyst by two-stage combustion. So, what happens is that we all know that from the in the gasoline engines you have three-way catalytic converter, and it requires a certain light of temperature in order to get activated, and then it starts reducing the HCCO and NOx emissions. When you have a GDI engine, what you do is you do two-stage combustion, and then the light of temperature is actually obtained very quickly, relatively much more quickly than conventional engines. So, you are actually putting out cold start emissions to a very small extent compared to conventional engines. So, that is one part. Then second part is that you increase the exhaust gas temperature and you design the exhaust manifold such that it sort of deaccelerates the flow. There is more time available for hot gases to do the heat exchange with the catalyst. So, that actually maximizes this effect, and then you put high volume EGR, and then EGR reduces the peak temperature inside the combustion chamber. So, NOx formation reduces, and whatever small amount of NOx formation reduces, you take care of it by using lean NOx catalyst. So, these are some of the features which I will be discussing in more detail. But coming back to the conventional stuff, so you can see this animation actually shows a carbureted engine. So, here you can see this is a carburetor, and this is where the fuel is coming. There is a throat here, the intake air, the petrol gets mixed here, and the intake air, it comes in the combustion chamber. So, this part is what is responsible fuel air mixing. The detail of this part is shown here. So, the air is coming in, and because of this throat, the pressure in this zone reduces, and here you have atmospheric pressure in the float chamber, and because here the pressure is less, here the pressure is more. Because of that, there is a spray through this channel, through this jet, the spray of fuel, and that fuel comes out in droplet forms, and then it mixes with the incoming air. And how much fuel air mixture has to be supplied is controlled by this throttle valve, and that is how this works. This is also explained in this figure, where you have a continuously reducing the cross sectional area, and then you have a low pressure zone, and then fuel gets incorporated. So, this is the conventional carburetor that is used for all kinds of engines that are used in the transportation system today. It could be a 2-stroke engine, it could be a 4-stroke engine, it could be a 2-wheeler, it could be a 4-wheeler or 3-wheeler. Most of the engines use this technology. Now, of course, if you look at the Indian scenario, the only 2-wheelers use carburetors. All the 4-wheelers have now been upgraded to the next level of technology, which is the multi-point port fuel injection technology. So, in multi-port fuel injection technology, you can see this is the intake port, and you have a separate injector. This is the intake valve. So, when the intake valve opens, there is a spray at that time, and this spray interacts with the air and fuel air mixture comes in. So, rather than working on vacuum and using a carburetor, you are having a solenoid injector which can actually be controlled much better compared to a conventional carburetor, and that is why this port fuel injection engine actually injects the fuel at 3 bar, and this is the formula which shows how you calculate the air fuel ratio, and this is the formula which shows how you can calculate the equivalence ratio. And when lambda is 1, it is actually a stoichiometric mixture. When lambda is less than 1, then it is a rich mixture, and when lambda is more than 1, this is lean mixture. So, most of the conventional car engines use port fuel injection technology, and now the trend is that you would like to, in order to generate more power more efficiently, the trend is that you try to put in leaner mixtures at high pressure. So, you use lean burn engine with turbocharging in order to control the emissions and in order to get higher thermal efficiency. So, this figure actually shows the transition of different technologies. On the x axis you have the year. So, and you see here in 1970s and 80s, carburetor was the only means by which the SA engines were working. Around 1980s, the port fuel injection was developed, and this development continued till 2000, and by 2000 almost all cars in the world were fitted with port fuel injection technology, including India. And then around 2000 this gasoline direct injection technology. Here you can see this is gasoline direct injection, that means the gasoline is directly being injected into the cylinder using an injector. So, this technology was developed by Mitsubishi, and now a large number of cars in the world, unfortunately not so in India, are using gasoline direct injection technology. So, just to reiterate, this is a carburetor where fuel comes in through a float chamber, air is coming, and this works on creation of vacuum in the intake manifold. In the port fuel injection system, you are injecting the fuel in the manifold, and then when the intake valve opens, the air fuel mixture comes in, and in a GDI engine the fuel is directly injected into the combustion chamber, only air is taken in through the intake valve. So, this is the subtle difference between these three systems. And now, let us compare these three systems and the progress that has been made over the period. So, here you see this is the air fuel ratio. So, this is the rich side and this is the lean side. So, obviously, you would like to move into this direction, as I said, and when you move into this direction you will also be moving in fuel economy terms. So, here you have higher fuel economy, here you have low fuel economy, here you have high fuel economy. So, this is where the carburetor is. So, that means carburetor works either on the rich side or very close to stoichiometric. Its fuel economy is not very good. Port fuel injection, it improves the air fuel mixture, that means air fuel ratio, that means it works on leaner mixtures and it gives you a better fuel economy. If you look at the diesel engines operate on overall very lean mixture and they give you much better efficiency, but GDI engine which operates on gasoline has actually much leaner mixture overall, and it actually gives you efficiency which are as high or even better than diesel engine. Coming to the power output side, you can see that this is 1980s carburetor power per liter, how much kilowatt or how much BMEP you can generate, and then here you have the port fuel injection. So, you can see the per liter power output from an MPFI engine is actually much higher than carburetor, and GDI engine, in spite of being more efficient and using lean mixture, GDI engine is able to give you more thermal efficiency, more power output. So, this is a win-win situation. So, you are not losing actually on any of the fronts that is required. This is another figure which shows the difference between PFI and GDI. So, in PFI you have this intake port here and the fuel injection is done in the intake, and this is the GDI engine. So, there is a cavity here and the spray is done when the piston moves down. Okay. So, this is the difference, subtle difference between GDI and PFI engines. Now, this animation shows clearly what happens. So, when the intake valve opens, only air is taken in and you can see a very peculiar shape of piston that actually rotates that actually changes the direction of the intake air. So, the direction changes, and then when the direction is changing you inject the fuel at that time. So, what happens is the fuel along with the air, it moves and gets concentrated very close to the spark plug and forms the mixture right in the vicinity of the spark plug. The spark is applied, rest of the areas are deprived of fuel. So, overall it is a very lean mixture, but very close to the spark plug you have just the right mixture at right time. When you apply the spark, the combustion takes place, and this actually animation shows in practice how the GDI engine actually works. Okay, so, if we look at the current situation with the, so this is the historical part. If you look at the current status of the gasoline direct injection engines, they are extremely popular in the road transportation system because of the advantages they offer. GDI engines are more powerful, GDI engine fuel economy is better, GDI engines emit lesser amount of carbon dioxide emissions, GDI engine emit lesser amount of carbon monoxide emissions, they emit lesser amount of hydrocarbon emissions, they emit lesser amount of NOx emissions, and their weight etc. is similar to conventional engines. So, what more you can ask for? This is these are the reasons because of which GDI engines or variants of GDI technology are very popular for in the road transportation sector, especially for car segment, mid-size segment. Carburetor and manifold system, as I mentioned earlier, they work more or less on the stoichiometric or very close to stoichiometric, but GDI engine works on very lean mixture, it is very efficient and very high power output, and overall the mixture is very lean, close to the spark plug the mixture is rich. GDI engine actually runs on actually two different modes. One is the stratified mode. So, when you are operating the engine under lean conditions or when you want to draw less power output from the engine, what you do is you inject very small quantity of fuel and that is injected and towards the end of the compression stroke, and it goes and gets concentrated very close to the spark plug, and as a result with very little amount of fuel you are able to generate part power output from the engine. So, on all part load conditions stratified charge operation is used. Suppose you are in a situation where you demand more power output of the engine from the engine. So, what is done is that the fuel injection from being in the end of the compression stroke, it shifts into intake stroke. So, when the air is coming in, at that time you inject the fuel, there is all the time available almost 150 crank angle degree or 200 crank angle degree to actually mix, and once you come to the close to the top dead center, then and that 150 to 200 crank angle degree is enough for formation of homogeneous charge, and when you apply the spark, the entire volume combustion takes place, and this is called homogeneous operation. It could be homogeneous lean if it is mid load. If you want full power output, then homogeneous stoichiometric mixture, that means you put full quantity of fuel into the engine combustion chamber. You will still have far better efficiency compared to port fuel injection engine. Okay, so, there is rich mixture in toto very close to the spark plug, there is high speed flame propagation because of the rich mixture, and sometimes in the other areas you burn leaner mixture. So, very close to the spark plug you have rich mixture, around it there may be either no fuel or very little amount of fuel forming lean mixtures. So, if you look at the schematic, so there are many types of gasoline engines. So, here this is centrally located injector and you can see the fuel is actually injected directly in the cylinder. So, the mixing of the fuel takes place in the combustion chamber. Overall mixture strength can vary from lean, which gives very high efficiency, to almost stoichiometric, which gives you high power output. There is formation of carbon dioxide, HC and NOx is very low from the gasoline direct injection engine. Fuel injection is pressure is much higher than port fuel injection engine. In port fuel injection engine, the fuel is injected at 3 bar. In GDI engine, it varies from 50 bar to 200 bar. In common rail direct injection diesel engine, the injection pressure ranges up to 1600 to 1800 bar. So, compared to diesel, this is much less, but compared to gasoline port fuel injection engine, this is much higher. And then here the best part is that you are actually using the motion of the air, which could be swivel motion or tumble motion inside the engine, which you are generating because of the special geometry of the intake manifold as well as because of the geometry of the piston. This helps in achieving your objective of the formation of homogeneous mixture, especially at full load condition. So, in the combustion chamber of a GDI engine, either you have a rich mixture or you have a lean mixture, you do not have a stoichiometric mixture. The possibility of knocking is the highest in stoichiometric mixture. So, because of this reason, neither the homogeneous lambda equal to 1 mixture does not exist, either it is lambda less than 1 or lambda more than 1. So, the possibility of knocking is actually much less here. Okay. So, if you look at this different variations of the GDI engine design, there are few of them that are shown here. So, as I mentioned here, if when the piston is coming up, end of the compression stroke, you are doing the fuel injection. This condition is stratified charge, that means you are operating the engine in this condition when you are operating the engine in part load condition. Homogeneous charge, that means when the piston is going down, you are injecting the fuel, you have lot of time available for mixing in all the entire combustion chamber, and this is where you form the homogeneous mixture, and this kind of condition is used for catering to high load conditions. There is a spray guided design engine combustion chamber where you have a spray and your spark plug is located very close to the spray. Then there is a wall guided GDI engine system where the wall of the piston and the cylinder is guiding the spray to come very close to the spark plug. And then there is air guided spray, air guided engine where air motion, the swivel motion and the tumble motion helps the fuel to come very close to the spark plug. So, these are the main different types of designs of combustion chamber of GDI engine. And so, as I mentioned, either you run the engine on stratified charge mode or you run the engine on homogeneous charge mode. When you run it on stratified charge mode, you can have higher compression ratio, you can have higher compression pressures because you are operating on lean mixture. So, thermodynamic efficiency is far better, and since it is a lean mixture, there is no possibility of pre-ignition or knock, and you are using overall leaner air fuel ratio. So, thermal efficiency and emissions are also very low. But when you operate the engine in homogeneous mode close to lambda equal to do the injection in the intake stroke, then you get more power output and then emissions are also low. So, if you look at the torque versus speed curve for a GDI engine, here the x axis shows the engine speed, y axis shows the torque. So, this is the condition in which lambda is much less than 1. That means, you are catering to low torque conditions and low speed conditions. So, when you operate in that, you are looking at mixture lambda less than equal to 1. So, that means you will be actually operating the engine end of the compression stroke injection conditions. And then you have homogeneous lean mode, that means mid load condition. So, this is homogeneous lean. So, you can see engine speed will be little higher, torque will be little higher, but still it will not be full load. So, here lambda will be more than 1, or if you are using EGR, then lambda will be equal to 1. Okay. So, in this condition you are able to meet a bigger envelope. So, that means more power output compared to stratified mode. So, this is the homogeneous lean mode. And then if you want to operate the engine at further higher speed and further more torque is expected, then you have no choice but to go for homogeneous mode where you do intake stroke injection. You can also use sometimes double injection. Here lambda is 1, or sometimes if you want to really produce lot of power, then lambda can be less than 1. That means, you will employ actually much lesser power output, much lesser, you will put in less amount of air and more amount of fuel. Lambda will be less than 1, that means the mixture will be rich. So, as I said, this is what is shown here, same curve which I explained earlier. This is the engine speed, this is the engine torque, and this is where you have less fuel consumption because the mixtures are lean. Overall air fuel ratio can be as low as 30 to 40. If it is a homogeneous mixture, you can't expect the engine to run, but since it is a heterogeneous mixture, you are doing end of the compression stroke conditions and very close to the spark plug, you have fuel air mixture fuel getting concentrated. That is why overall, in spite of being overall 30 to 40:1, you are able to operate. In the superior output mode, you need high power and high torque. You are doing intake stroke injection, and here the air fuel ratio can really vary between 13 to 24. 15 is the stoichiometric mixture. So, you can see if it is homogeneously lean, it could be 24 for catering to mid load, mid speed conditions. If it is full load, full speed, it will be 13 to 18 kind of a air fuel ratio. Okay. Now, compared to GDI engine, compared to PFI engine, the GDI engine have much better volumetric efficiency, and that also helps us in getting more power output. So, here the curve shows engine speed on the x axis, volumetric efficiency on the y axis. You are injecting the fuel in the port, and so this is the volumetric efficiency of the conventional port fuel injection. In a GDI engine, what happens is that when you are either in the intake stroke or in the end of the compression stroke, you are injecting the fuel directly in the cylinder. It is in liquid form, and once you inject the fuel, it has to vaporize, and once it starts vaporizing, it will absorb latent heat of vaporization, and it will bring down the charge temperature. As a result, the charge density will increase, charge will shrink, and therefore it will actually suck in more amount of air into the combustion chamber, and as a result you will be having higher amount of air in the combustion chamber, and that leads to increase in volumetric efficiency. So here you can see this is the volumetric efficiency for GDI engine, which is higher by roughly 5% compared to conventional port fuel injection engine. So, so this is the main difference between these two. So these are all positive things, but so there are certain limitations also. So the limitations include, that there is sometimes there is difficulty in finding space for an injector to be mounted in the port. You have to have, so if you have a 4-valve design, in each cylinder head you will have 2 intake valves, 2 exhaust valves, 1 spark plug, and on top of it you have to find space for 1 extra injector, and that can really be challenging. So you can find that space very easily in 2-valve engines, but 2 valve per cylinder, but in 4-valve per cylinder it could be a little bit of a problem, and so head design becomes challenging, and then you will, because of the challenging head design, you will be adding cooling issues. So cooling of the cylinder head will be challenging, casting of the cylinder head will become more complicated, and there are more refinements required for idling, and there is greater need for control of emissions, because most of the GDI engines are expected to meet Euro 6. So emission control has to be perfect. Combustion chamber design and control of GDI is rather complex, because GDI engine actually is very difficult to manage GDI kind of a combustion without the use of sensors. You need a very huge suite of sensors and ECU. Okay. So the development challenge of the GDI include it's difficult to control the stratified conditions. It's complex injection technology changes, or injection pattern changes with load changes in low speed conditions and low power conditions. You are actually injecting during the end of the compression stroke. In high load and high speed conditions, you are injecting during the intake stroke. So this injection, when you want to do injection, becomes dependent on how much accelerator you are pressing, and that makes this whole control more complex. You are injecting the fuel in liquid form inside the cylinder, so the injector really remains cold, and rest of the things inside the combustion chamber are hot. So there is a thermophoretic pressure on all the particles that are generated. They deposit on the injector, and there are a lot of problem with injector deposit, and sometimes even if you have liquid droplets going into spark plug, the spark plug can actually get fouled, and so sometimes if you don't design your system properly, you maybe end up frying the spark plugs quite frequently. There could be a problem of unburnt hydrocarbons. If you don't design it properly, the NOx emissions could be high, and obviously since you are putting lot of fuel and there are fuel rich regions inside the combustion chamber, particulate emissions from gasoline engine, gasoline direct injections could be a real problem. I mean, you will be amazed that PFI and carburetor engines do not have a problem with particulates, but in this case of GDI engine, particulate emissions is a real challenge to tackle, and this is probably one of the biggest challenge. All other things are very easy to control, but this is quite challenging. 3-way catalysis cannot be utilized to full advantage. This is also one of the challenge. You have increased electrical power and voltage requirements for injectors and drivers, because everything has to be electronics controlled. With the introduction of ECU and electronics in the engine, GDI engine is possible, but that makes it quite complex. And then, as I said, Mitsubishi has most of the patents, but the other companies are also filing their patents, and if you want to develop this technology on your own, either you have to lease the patents for other companies, or it is possible that you may actually get into a conflicting situation with them, and it will increase the cost of manufacturing a GDI engine if you have to really pay very high for patents. So this is one of the limiting factors. So the major objectives of the GDI engine, as I said, are first is that you want ultra low fuel consumption compared to even diesel engines. The GDI engines have to be much more efficient, and then you also want superior power compared to PFI engines. So these are conflicting. You want to get more power output, but you do not want to invest so much of energy. You want the fuel consumption to be further lower on a per kilowatt hour basis. So, I think I have already explained the difference between MPFI and GDI very clearly, and I think I have also explained the features of GDI. So, I will skip it. So, now let us look at how we really make it happen at a technical level. So, now I will explain the details of what are the features, distinguishing features of GDI, which makes this whole concept possible. So, as I said, there are two combustion modes. First mode is stratified charge mode, which is also called ultra-lean combustion mode. Second mode is homogeneous charge, which is called superior power output mode. So, under normal driving condition, when you just started the engine or when you are just running at low load, low speed conditions, you want to operate on ultra lean mode. That means you will do the injection of the fuel towards the end of the compression stroke. And if you want superior power output mode, that means you, when you are accelerating or when you are going on a highway at a very fast speed and you need more power output, at that time you inject the fuel in the intake stroke and you form homogeneous mixture. So, this is very similar to what you see in a port fuel injection engine. So, this is very similar to port fuel injection. The only difference being that you will produce more power than PFI engine. The reason being that you are injecting the fuel directly in the cylinder, that will cool the charge, and as a result the density will, charge density will increase, and you will be able to put in more amount of fuel air mixture into the cylinder, and from the same cylinder volume you will actually be getting much higher power output in a GDI engine. So, this actually figure explains. So, here you are dealing with part load condition. As I said, you inject the fuel during compression stroke, you have stratified fuel air mixture. So, piston is moving up, you are injecting the fuel very close to the spark plug, it gets concentrated. Other regions of the fuel combustion chamber do not have any fuel. And so, overall if you look at it, it is a ultra lean combustion, but in this zone you have sufficient amount of fuel air mixture, and this gives you combustion takes place here, and this gives you enough power to cater to low power, low speed, low power output needs. Okay. But you are actually consuming very less amount of fuel, because there is hardly anything. You are not filling the entire combustion chamber with fuel air mixture, just like doing a port fuel injection engine. So, that makes it extremely low fuel consumption compared to PFI engine. In the high load conditions, you are doing intake stroke injection. That means when the piston is going down, your injection starts. So, when injection starts, then the piston starts coming up. This whole volume is filled with homogeneous mixture. So, you have a homogeneous mixture which is very close to lambda equal to 1, and it leads to stoichiometric combustion, and then as I said, because of the increase in volumetric efficiency, you are able to get more power output than a conventional engine. You are actually able to control precisely the air fuel mixture much better than carburetor engine, because of the use of lot of things. So, one is that you use a concept called wide spacing. That means the injector and the fuel, injector and the spark plug, these are quite at a distance. So, when you do the injection, there is a quite a distance, and then this distance allows you to control the air fuel mixture strength. So, injection of the fuel spray occurs farther away from the spark plug than in a conventional petrol engine, and it creates a wide space that enable optimum mixing of the gaseous fuel and air, and therefore, you are able to in a way control the fuel air mixture strength. So, in stratified combustion, fuel is injected towards the curved top piston rather than towards the spark plug, and during the later stages of the compression stroke, the movement of the fuel spray, the piston head's deflection of the spray and flow within the cylinder causes the spray to vaporize and disperse. So, you have the piston like this, the fuel is injected, air is moving in this direction. So, along with the air the spray moves, and it becomes since the air is hot at the end of the compression stroke, the spray vaporizes, disperses, and this results in mixture of gaseous fuel and fuel air mixture formation of adequate strength, and then that mixture is carried to the spark plug, and then spark is applied. So, the biggest advantage of this system is that it enables precise control of the air fuel ratio at the spark plug at the point of ignition. So, you are essentially controlling the spark plug in the vicinity of the spark plug, you are controlling the air fuel ratio. In other areas around it, the air fuel mixture is relatively much more lean, and that is what makes this GDI engine very unique. Okay. So, you can see here there is a lot of space between injector and spark plug, and what happens is this piston is quite hot. So, when the spray jet hits, part of it is wetted here, and this wetting of liquid fuel, it absorbs the heat from the piston and then it vaporizes. And because there is tumble motion also happening, because there is a intake valve, and because this intake valve the air is moving. So, because the tumble motion, all this fuel that you have injected and it has vaporized, everything gets concentrated in this zone. Rest of the areas there is no fuel, and that is what makes it very, very efficient. It gives you better fuel efficiency. This concept of wide spacing makes it possible to achieve stratified mixture, and then this GDI engine therefore becomes more stable, ultra lean combustion is realized, and it allows a significant improvement in fuel economy. In addition to GDI lean combustion, GDI engine achieves higher compression ratio. As I said, in the GDI engine, you are either dealing with relatively richer mixture or relatively leaner mixture, and both of them avoid knocking, and therefore you can use actually higher compression ratio without the fear of knocking, and therefore you can get even further improvement in thermal efficiency and fuel economy. So, these features actually reduce the fuel consumption. In fact, just if you quantify, fuel economy of the GDI engine is 33% or more better than comparable port fuel injection, which is a significant improvement. So, if a port fuel injection of 1.5 liter gives you 12 liters per 12 kilometers per liter, GDI engine of the same capacity will give you 16 kilometers per liter, and that is a significant improvement. You will be also reducing CO2 emissions by 33%. So, this is what is shown here. So, this is 12 liters from 12 kilometer per liter from a PFI engine, and this is 16 kilometers per liter from a GDI engine. In addition to fuel economy, there is improved power output from the engine. So, in high load operation, charge burn in homogeneous mixture mode, and GDI engine just functions like any other port fuel injection engine. Because why? Because you are doing the intake stroke injection, and then everything is homogeneous just like PFI. But in spite of all that, it achieves significantly higher power output. Why? Because when you inject the fuel in the intake stroke, you are making the mixture much colder. It is much colder because the vaporization of the fuel takes place, and the mixture becomes more dense because of lower temperature, and as a result more fuel air mixture is taken in. Volumetric efficiency improvement takes place, and because of the improvement in volumetric efficiency, the power output from the GDI engine also becomes higher, and then this happens while you are preventing knocking. So, in high load conditions, a homogeneous mixture is used to prevent partly dense mixture that forms soot to form. So, what happens is this is knocking is fine, you are getting more power output, but when you have very rich mixture close to the spark plug, you land into another trouble, and that trouble is that because of this rich mixture you will form soot, and now you have a problem to deal with soot. You have taken care of knocking problem, you have taken care of power output problem, but then you run into another problem which is called soot formation problem. So, this is actually taken care by two-stage mixing technology. So, two-stage mixing technology, I will just explain what this two-stage mixing technology is. Suppose you have to inject 20 milligrams of fuel to cater to a certain load conditions. So, in two-stage mixing technology, what you will do is you will inject 5 milligrams during intake stroke. So, what that 5 milligram will do is it will form a very lean mixture which is not possible to burn on its own. So, very lean mixture, but it is homogeneous all around the combustion chamber, and the 75% fuel you will inject at the end of the compression stroke. So, when you inject it, combustion will take place, obviously everything will get concentrated very close to the spark plug. So, combustion will take place, power output will take place, but soot formation will also take place because this mixture is much richer than stoichiometric. You do not have enough air. So, not all the hydrocarbons will burn, there will be partial combustion of the fuel, and as a result soot formation will take place. But this soot will then move to neighboring area where you already have some amount of fuel available. So, when this soot moves, that mixture will not burn, but when the soot moves, the air fuel mixture strength increases and soot burns, and that fuel also burns in the neighboring area. So, this is two-stage mixing. That means you are mixing the fuel in two ways, 1/4 of the fuel in the intake stroke and 3/4 of the fuel in the end of the compression stroke. This way you can suppress the transient knocking, okay. This way you can suppress the soot formation, you can get higher output, power output and so on. So, this is what is shown here. This is the intake stroke, piston is moving down as you can see, 1/4 of the fuel is injected, you can see pulse is very, very small in the intake stroke, 1/4 of the fuel is injected. This fuel forms a very lean homogeneous mixture inside the combustion chamber. Then during the compression stroke, at the end of the compression stroke, you do another injection where 75% of the fuel is injected. This fuel gets concentrated very close to the spark plug, and then you apply the spark. The spark is applied here, and as a result this whole of the combustion chamber gets ignited. It leads to suppression of knocking, this leads to formation of less amount of soot and so on. Okay. So, if you look at this technology to directly control the soot formation, this is the first time in the long history of petrol engines, 125 years, that the direct control of the combustion has been used to suppress knocking, and also it further underscores the importance of achieving precise control of the air fuel mixture in the engine. So, that is very, very important, that is what is achieved by GDI engine and because of its electronic controls. So, this is how the suppression of the knocking takes place. So, this is the first case where you have only compression stroke condition. So, as I mentioned 20 milligram of fuel for example is injected, and here you have fuel injection. This is the zone where the combustion the fuel air mixture will be very rich, combustion takes place, but there is not enough air. So, you will have formation of soot. This soot will move into neighboring areas, but it will not be able to burn because the amount of fuel that is there in the soot is very, very little, and therefore, it will the composition will get frozen, and when your engine will start giving you a sooty combustion, and you can see smoke coming out of a GDI engine in spite of very good efficiency. The two-stage mixing concept which I explained. So, this region, most of the combustion chamber is very, very lean, ultra lean mixture present. You inject the remaining fuel. If the soot form, obviously the soot will form here because it is a rich mixture. It moves into this neighboring zone, already some fuel is present, more fuel comes in the form of soot, and this is where the reignition of the fuel air mixture will take place. Okay. So, this is as far as the soot control is concerned. But as I said, these days one of the biggest challenge that the automotive manufacturers face is the emission compliance all over the world, including in India. In India now we are trying to go to Euro 6, and for Euro 6 BS 6, Bharat stage 6, the emission norms are very, very tight, especially for HC, CO, NOx and PM emissions. And if we want to introduce this GDI engine technology in India, obviously it has to comply with all the existing emission regulations and also the emission regulations that will be coming in future. And for that, what we need to do? We need to control all these 4 species. So, I have already told you how direct control of particulate formation can be actually done, but in spite of that, all this technology there will be some particulate formation, and for that you will probably need a gasoline particulate filter to actually remove. You can either use gasoline particulate filter or some kind of a particle filter you have to put in. Okay. Now, this is one schematic which shows the engine. So, this is a GDI engine. So, what you need to do is you need to control HC, CO, NOx and PM. So, this can be done by two-stage combustion. Okay. So, because of two-stage combustion, this controls the GDIs, this controls basically the formation of air fuel mixture, as I mentioned. Then what you can do, two-stage combustion is a technology by which when you start the engine in the beginning, the exhaust gas temperature is relatively very low, it could be 200 degree, 150 degree. But all of us know that in a spark ignition engine, when we apply 3-way catalytic converter, it has to be heated to 250 degree centigrade, that is the light of temperature for the catalyst. That means, when until and unless you achieve 250 degree centigrade catalyst temperature, whatever CO, HC, NOx is forming inside the combustion chamber, it will be going out into the combustion out of the combustion chamber in an unabated manner. It will be going into the atmosphere, polluting the environment. So, what is really required is that, is it really possible that normally it takes about 200 seconds to achieve 250 degree centigrade temperature once you start the engine. So, in 250 seconds, you know, you will be putting in a lot of HCO and NOx. Is it possible somehow to reduce this 250 seconds to say 50 seconds? Is it possible? So, the answer is yes, it is possible, and it is achieved by two stage combustion, and this is the feature of GDI technology. How it is achieved? And this is only, so this is achieved by actually doing whatever you are doing, plus you know, you inject small amount of fuel in the exhaust stroke. So, when you do exhaust stroke injection, obviously you will not be producing any power output, but you will be heating the exhaust gas. So, the exhaust gas which was 200 250 degree centigrade will now become 800 degree centigrade. So, obviously if you have a catalyst which is taking 200 seconds to get heated up, now when it is exposed to 800 degree exhaust, it will be quicker to heat it up. So, light off will be quicker, and this injection needs to be done only for first 20-30 seconds once you start the engine. So, it is a non work producing energy, that fuel that you have to inject, but it is only limited to first 20-30 seconds. After once the catalyst is heated, you do not really need to put any extra fuel into the exhaust stroke. You can just stop that injection. So, that is the two stage combustion, okay. And that helps the activation of the three-way catalytic converter, this three-way catalytic converter here, okay. And there is a special type of, you know, manifold. So, what that does is it kind of reduces the speed of the flow of the exhaust. So, it allows more time for the heated gas to interact and heat up the catalyst. So, this using this reactive type manifold, the time can be further reduced, and of course, you use EGR. If you do high volume EGR, you can reduce the NOx emissions to a great extent. Whatever NOx formation takes place in spite of EGR, you can take care by this lean NOx catalyst. So, if you look at the entire experimental setup or the setup for this GDI engine, you are having high volume exhaust gas. That means from the exhaust you will take some of the exhaust gas back into the intake, and this exhaust could be very high. This will help you reduce NOx emissions. Then you have injection at the end of the compression stroke, because this is idling, okay. So, it is a lean mode combustion, and then you have second injection in the exhaust stroke that will heat up the combustion chamber and exhaust gases, and these exhaust gases will be coming to the reactive type manifold, where they will heat up the three-way catalyst as well as lean NOx. So, using all this, you can see a suite of technologies, you can actually control all four types of pollutants that are coming out. So, if you look at the reducing the HC emissions, combustion occurs towards the end of the compression stroke and conclude in the beginning of the expansion, and by which time the gases in the engine rise to a very high temperature. At this time, the fuel is injected again towards the end of the expansion or in the beginning of the exhaust. As a result, the temperature further rises, and you know, gas temperature rises to 800 degree centigrade compared to about 200 in case of idling immediately when you start the engine from cold. So, this actually helps you increase the temperature. So, this is the two stage combustion. You can see this is the compression stroke. You are injecting the fuel. It's a, you are just starting the engine, so load requirement is low, and therefore you are injecting the fuel at the end of the compression stroke. Combustion starts here, combustion gets almost completed, and towards the end of the expansion stroke and beginning of the exhaust stroke, you do another injection, which is of course not going to contribute towards power output, but it will heat up the exhaust gas, and because of this heated exhaust gas, the activation of the catalyst will be very, very quick. Catalyst activation temperature for three-way catalyst is approximately 250, and two stage combustion and use of a reactive type exhaust manifold, you can increase the effectiveness of the heating of the catalyst process, and this is going to actually help you control the HC and CO emissions to a great extent. Now, as I said, EGR is also another technique that can be actually used to control the emissions. So, if you look at this on the x axis, you have the EGR. So, EGR normally 0% to 60% EGR is possible, but if you look at the conventional combustion, if you put in conventional SI engines, if you put anything more than 15% EGR by volume, NOx reduction is quite significant, 30–40%, but beyond this point, the normal PFI engine will have a problem, because there will be combustion related issues, there will be unstable combustion and so on. But in a GDI engine, you can go to as high as 60% EGR, and as a result you can reduce as much as 90% NOx. So, compared to conventional engine, NOx reduction is much higher from a GDI engine because of the use of very high volume of EGR. Such a high volume of EGR up to 60% is not possible in a port fuel injection, but in a GDI engine it is not at all difficult, it is possible. Okay, so, using all these technologies, the GDI engine becomes extremely clean. You can control HC, CO and NOx because of the three-way catalytic converter. You can use another lean NOx trap to actually trap whatever NOx is formed. Then you can probably, using in cylinder control of pollutants, particulates formation you can do, and on top of it you can actually deploy a gasoline particulate filter in order to remove whatever small amount of particles have been formed. So, this way GDI engine in summary emerges as a technology for future, which has very high economy, you can get much higher power output, and you have very low emissions of HC, CO, NOx and PM, and this is one technology which is a technology for future for India, and it should be accepted by the Indian automotive sector wholeheartedly. This is the future. You can reduce greenhouse gas emissions to a great extent, you can increase the fuel economy to a great extent. Thank you very much.